Hello everybody. In this lecture I'm going to go through second part of the thermochemistry or thermodynamic, and if you are Chem 1414 student, chapter it will be chapter 10, but for science major student or pre-med students usually you will be taking this one in Chem 1515, and it depends which edition of the book you have. It can be around the chapter 18 or 19. Okay, so last time in the first part of the thermochemistry we went through stuff like heat. We said heat under constant pressure, we call it delta H. Next one, heat under constant volume, we call it delta E. Delta H is equal to delta E plus P delta V. So in order to have delta E equal to delta H equal to delta E, we need to have a correction. And if that correction is equal to 0, then those two, they will be equal to 0. They will be equal to each other. Otherwise, delta H is not going to be equal to delta E, because sometimes when we spend heat or we get heat, that heat it can be taken by the gas molecules, and their volume can go up and down. And if we have change with volume, then here, if delta V is not equal to 0, that means V2 is not equal to V1, then we have work. Work is equal to minus P delta V. So sometimes when we are spending heat or we are getting heat, that heat it can be used to do work. Okay, and this is minus of work. Okay, and also we went through a couple of formulas. One, we said delta E is equal to Q plus work. Next one is Q, you can calculate it through C delta T, heat capacity, multiply change with temperature, or Q equal to MCS delta T. Mass multiply specific heat capacity multiply delta T, change with temperature. How about work? I just mentioned the work there. Work is equal to minus P delta V. So we can calculate the work, we can add it to heat, and we can get the delta E. Next one is, we said delta H, we can find it through knowing heat. If heat is under constant pressure, then we got the delta H. The unit here is going to be either joule or kilojoule. Joule or kilojoule. But if you want to calculate delta H for a reaction, delta H for a reaction, a specific reaction, let's say you have a balanced reaction. Okay, you have a balanced reaction. Example, H plus OH, you get H2O liquid, and you want to know the delta H of this reaction. In that case, you need to know number of mole for the limiting reagent. Okay, so you go with heat under constant pressure, divide by number of mole. In that case, you get joule or kilojoule per mole. Okay, so anytime we write delta H in front of any reaction, we need to divide it by number of mole of the limiting reagent. Then I showed you that delta H is the gap between reactant and the product, the energy of the reactant and the product. So delta H, you can calculate it through delta H under standard condition. You can calculate through number of mole for the product multiply sorry, delta H of the product under standard condition minus number of mole of reactant multiplied delta H of the reactant under constant standard condition. Under standard condition. Okay. Where can I find delta H of the reactant and delta H of the product under standard condition? Okay. You need to have this. If you're talking about temperature, should be 298 Kelvin. If the pressure 1 atmosphere. And if you're talking about concentration must be 1 mole per liter. Okay. And you have the most stable phase of that element. The most stable of the element, you will treat it as a reference, and you compare them. You compare energy of the new compound that you made with the reference, and then you will get the delta H for it. Okay. So this chapter, we're gonna go through second law of the thermodynamic. Okay. So we had law of conservation of energy. You cannot create or destroy energy. It's kind of law of conservation of mass. When we say if you start with 10 gram, you have to get 10 gram at the end. Okay. You don't create or destroy mass. Okay. And then first law of thermodynamics was saying that total energy of the universe is a constant number. The total energy of universe for universe is going to be equal to energy of the system plus energy of the surrounding, and this one is a constant number. And we said if you get first derivative from it, this one will be 0. You get change with energy of the system plus change with energy of the surroundings. So we're gonna get this delta E of the system equal to minus delta E of outside. Okay, so the first law again is saying that total energy universe is a constant number. If that's true, then delta change with energy of the system is going to be equal to minus change with energy of outside. Second law of thermodynamics. Second law is talking about entropy, and we need to discuss entropy. We need to know what's the entropy first. Entropy is something that talking about randomness technically. What I mean by randomness, you want to know how messy the system is. The more freedom, again, the more freedom you give to the system, we say the higher entropy that system has. Okay, so in this case, I have two balloons, two flasks, whatever you treat them or you call them. One is empty and the second one is full. That's not natural. Okay, this is not natural. Something like it does not happen by itself. We force it. Okay, we force it. Because we force it, I'm going to say this one does not have much of freedom. If you open this valve, you see the molecule start to move to the right side until they fill it. Okay, they fill that one. So in that case, I say this one, it can happen. Okay, if I open it, that one, it can happen. And you see here, we open it and it did happen. In that case, here, this one says if I compress them or force the molecule to go that side, I can do it. It's not impossible. I can do it. Force the molecule to move this side to the left one and then close the valve. It's possible, but naturally does not happen because it costs some energy, and the system it will be unstable. So that's the reason we say this is not natural thing. Okay, so entropy is telling you that how much of freedom you have. The higher freedom you have, the higher entropy you will see. Entropy is a state function. That means similar to E, H, temperature, pressure, or volume, change with entropy does not subject, or it's not subject to a way you do the process. It doesn't matter, like how you got to, for example, how did you get from here, from the left one to the right one? Okay, I don't care about, was it slow, was it fast, you did it in a second. We don't care. We say if we want to calculate the change with the entropy, we say give me entropy of this, the final entropy of the initial, and I'm going to subtract them. It will be S2 minus S1. That one is going to give me the change with the entropy. That's a nice thing with entropy, because it's a state function. Okay. So the second law of thermodynamics says total entropy of the universe increases in a spontaneous process. If you have a reaction or process that can happen by itself, you don't need to get involved with that reaction or process. If you have such a process, and that process can move forward, or it can happen by itself, then we say that one is a spontaneous process. In order to do it, we need to have a driving force. Driving forces can be like a system got stable. How? By releasing heat, by increasing entropy. We need to have something. We need to have something that we call it driving force. And in this case, it's going to be here, entropy of the universe. If that one is, if that one, the total entropy is getting a positive number, turning to a positive number, that's a good one, because you have a system that it has higher freedom. Okay. We have delta S universe equal to delta S of system plus delta F of surroundings. If those two are equal to 0, we say we have reversible. We have process. It can move forward or it can get back. So it's possible to generate a product or turn it back to reactant. But if you add them, okay, and the number was positive, more than 0, that's a one-way process. That process cannot get back by itself. Okay, and we say this one is irreversible. Okay, entropy increases by moving from solid to liquid and then to gas. Okay, so if you have H2O solid, okay, ice, you turn it to H2O liquid, say water. Then you turn it to gas. Still, in this case, I will say the entropy is increases. Entropy of the solid less than entropy of liquid. That one less than entropy of gas. Because in order to move from solid to gas, we need to add heat. We are adding heat. What's the role of heat? Role of heat. Heat will be used to get rid of or decreases the interaction between molecules. Okay. We had solid molecules. They were well packed and close to each other. There was a tiny vibration, a vibration of the molecules just around itself, and they don't move really far from their neighbor. We gave it heat. Now turn to liquid. They can move around one molecule, like when you drop a paint, or you drop like say food color, whatever, you drop it in a glass, you can see the paint start moving inside that glass. They can move. Okay, so there is more freedom than solid, but still is attaching to the surface. I can see it is somewhere around the surface. It can't get out of the surface. And so I'm not going to say 100% freedom. And then when you turn it to gas, this time they can go anywhere. We say we have higher freedom. Higher freedom, because we have higher freedom, we can, or we have the right to say entropy is higher. Okay. Entropy is higher. So entropy goes up by moving from solid to gas. And next thing is, if you want to know entropy in two molecules, or you want to compare entropy of two molecules, look to their molar masses or size. Okay, molar masses or size. Okay, let's say we have helium. I want to compare it with neon. Okay. I know when I move down in one group, when we go down in one group, size increases. Okay. So group 8, we have helium, and then we will have neon, then argon. This is a group 8 or 18. When you go down inside the group, size increases. So I can say size, the right side of the periodic table decreases, down in any group increases. You don't know the trend for the size, that's fine. We can focus on the molar masses. Molar mass of helium, as for helium, is around 4. Molar mass of neon, I believe it's 20, but let me double check this one. Molar mass of neon is, yes, 20.18. So this one is around 20. Again, unit gram per mole. So I'm going to say entropy of helium is less than entropy of neon, because molar mass of neon is higher. Why entropy is getting bigger by increasing size or molar masses? Okay, let's talk about that. We have helium and neon. Helium, you have a nucleus with 2 protons, and first orbit you have 2 electrons in it. Neon, you have nucleus with 10 protons. First one, you have 2 electrons. Then you have the second layer with 8 electrons in it. As you increase number of electrons, repulsion is going up. So now we have more repulsion. Because we have more repulsion, size is gonna get bigger. Okay. If you measure this one and you call it R for helium, we have here first layer, and that one is the second layer, R of neon. R of helium is smaller than radius of neon. Why? Because this one, in the electron of first layer, is close to the nucleus, and it can feel the positive charge of the nucleus directly. So there is huge electrostatic interaction between them. I can say this electron has a less freedom than electron that's sitting inside second layer. Because this one, electron that's sitting inside second layer, is way far from nucleus, at least by 1 layer more. So I have the right to say this electron that belongs to second layer, has higher freedom, and because it has higher freedom, it can move anywhere. Okay, now that it can move, like around nucleus, or maybe we should not say anywhere, it can move a distance a bit longer, or way more, or far more from electron of helium. So I have the right to say entropy of neon higher than entropy of helium, because these two electrons are far from the nucleus. You want to bring them close to the nucleus, that's fine. Apply force. You apply force, but when you apply force, these two electrons will feel inner electrons. And remember, electron-electron interaction is repulsion. So you can't really bring them too close to the nucleus. They will build repulsion with inner electrons. And that's the time that we cannot bring them anymore, close to the nucleus. So we have to let them go a bit far from the nucleus. And that's the reason I say entropy is higher by an increasing molar mass or size. One more about the molar mass and size. You have CH4, C2H6, and C3H8. Last one. Molar mass for methane is around 16. This one around 30. And here we have 36 plus 8, 44, around 44 grams per mole. Okay. As we increase the molar mass, then entropy is going to go up. So I'm going to say entropy of C3H8 is higher than entropy of C2H6, and that one is higher than entropy of CH4. Okay. Because molar mass of propane is the highest, it will have the highest entropy. Okay. Why it has highest entropy? Not only because the molar mass, look at the number of bonds that we have. Okay. I can stretch this bond and keep the rest as they are. Play with that bond or play with a couple of them. I have more freedom, or I have, I can distribute the energy in different bonds, different way. I can, stretch this bond. For example, I can stretch that one, bend those, and still have plenty of options there. Okay. The more bonds you have, the higher chances you do have to distribute the energy. So we say entropy is going to be higher. But frankly, don't go far with that one. You want to follow, or you want to understand which one it has higher entropy, just simply look to the either size or molar masses. Okay, I can go deep with this one, but you need to have something about vibration. What type of vibration have? We have stretching, we have bending vibration, and I'm not gonna go in deep with those. So at the beginning, I said S, or entropy, is a state function. Okay, so entropy is a state function. If that's true, then we should say entropy, change with entropy is going to be equal to entropy of the final point minus entropy of initial point. So I should be able to calculate change with entropy under standard condition by using this fact. I need to know entropy of the product and entropy of the reactant. I will subtract them, and that one, it will give me entropy of the change with the entropy. So I'm going to say change with the entropy under standard condition on any reaction is going to be equal to number of mole of the product multiply entropy of product minus number of mole of reactant to entropy of the reactant under standard condition. Please look to SP and SR. I did not say change with entropy of reactant or product. Okay, I did not use those two. What's the reason behind? For delta H, we said number of mole of product multiply change with the entropy of the product minus number of mole of the reactant multiply change with entropy of reactant, or delta H of reactant under standard condition. When it comes to delta H, we have a reference. Okay, we have a reference, we have a base, and that reference, it has delta H equal to 0. Okay. So the reference, whatever we are talking about, the most stable phase of that compound or element, it will be the reference. Like nitrogen, the most stable phase for nitrogen is going to be N2 gas. So delta H of N2 when it's gas is going to be equal to 0. We do not have such a case when it comes to entropy. Any compound you pick, it has entropy. There is no compound with a 0 entropy. So that's the reason I'm not saying delta S of the reactant a product, and here delta S of the reactant. Simply I'm saying entropy. So you can't say this one equal to 0, whether reactant or product. That's not true. You can't say that. Okay, we have a reaction. Here's the reaction. It says C2H5 OH liquid. We add 3O2 gas. We get 2CO2 gas plus 3H2O liquid. Sorry, gas. Yes. Let's say find delta S of this reaction. Find delta S of the reaction, and they give us delta S of each compound. S here is 160.7 unit joule over mole to Kelvin. O2 is not 0. O2 is not 0, it's 160.9. CO2 213.7, 188.7. So delta S for the reaction, is going to be number of mole of product multiply delta S of, S of product minus number of mole of reactant to S of reactant. So I got delta S of the reaction equal to product. We have 2 multiply S of CO2 plus 3 S of H2O minus 1 S of C2H5 OH plus 3 S of O2 and close it. So delta S of the reaction will be 2 multiply 213.7 plus 3 multiply 188.7 minus 160.7 multiply 1 plus 3 multiply 160.9. And I will close it. I got, so I have 2 multiply 213.7 plus 3 multiply 188.7 minus 160.7 minus 3 multiply 160.9. I got 350.1 delta S after reaction equal to 350.1. Let's double check it. And unit, we go with joule over mole to Kelvin. Okay. Now that we know how to calculate entropy for a reaction, we can talk about change with entropy of exo and endothermic reactions. So let's say you have this. First one, you have exothermic process. So heat is going out. We are losing heat. So I'm going to say minus heat. Heat is going outside. So if you say here, T1 of the system, T1 of surrounding. T1 of the system is going to be less than T2, it's going to be higher because it's exothermic. It's going to be higher than T2 of the system. We have a system. Our system is giving heat. It's giving heat to outside. So outside is getting heat. So T1 of outside is going to be less than T2 of outside. Outside got heat. System lost heat. So we can say here, our system lost heat minus heat. Outside you add heat to it. Okay. So if your system lost heat, it's getting colder. And because it's getting colder, change with entropy of the system will be a negative number. Outside got heat. Like you are burning a propane. Propane is going to heat your kitchen. And temperature in your kitchen is going to go up. So we say change with entropy of outside, it will be a positive number. Okay. In endothermic process, system is gaining heat. Outside is losing heat. This is outside. Outside is negative. So temperature, final temperature of the system is higher than initial temperature of the system. So our system is getting warmer. That means entropy, it will be a positive number. Change with the temperature of outside. This time is going to be negative. Outside is losing heat. So T2 of surrounding less than T1 of the surrounding. So you can say change with entropy of outside or surrounding. It will be negative number because we lost heat. This one is getting colder while the system is getting warmer. Okay. How can I calculate this? If this one is equal to 0, we say reversible. If it's bigger than 0, positive number, we say irreversible. I need to know what's the delta E of the system, and same thing for outside. And the problem with outside, we do not have control to outside. Usually outside is bigger than us, and surroundings bigger than us. Because it's bigger than us, so it's hard, really hard for us to calculate the change in entropy or energy in it. But there is a way to figure it. I know change with energy of the system is equal to minus change with energy of outside. And I know heat of the system equal to minus heat of surrounding. So I'm going to focus on the system, try to get the entropy for the system, and also I'm going to try to figure how much heat we gave to outside. Because if we have that one, we can calculate heat, we can calculate change with entropy of the outside. Change with entropy of outside, we can get it through this. Here, minus Q of the system divided by T. Or you can say Q of the surrounding divided by T. We don't have this part, but we know it's going to be equal to minus Q of the system. So I will use this one to calculate delta S of the system. And next thing, Q of the system under constant pressure is going to be equal to delta H. Okay, so Q under constant pressure for the system will be equal to delta H of the system. Delta H of the system. So delta S of the surrounding, instead of minus Q of the system, I'm going to say minus delta H of the system divided by T. I will use this formula to calculate delta H of the system. I know how much heat went outside, or we got it from outside. I give it negative sign because of this. Give it negative sign, so then I can calculate entropy of the surrounding. We have a reaction that it says N2 gas plus 3 mole H2 gas, we get 2 mole NH3 gas. Delta H of this reaction is equal to minus 92.6, so it's 92.6 kilojoule over mole. Delta S of the system minus 199 joule over mole to Kelvin, and the temperature is 298 Kelvin. So now use this info and figure whether the reaction is spontaneous or not. Spontaneous or non-spontaneous. We need to know this. delta S for the universe will be equal to delta S of the system plus delta S of the surround. This one must be a positive number based on the second law of thermodynamics, and then it will be spontaneous. Okay. So it has to be positive, then the reaction it will be spontaneous. We do have delta S of the system, but we don't have delta S of outside. So now let's go after it and find delta S of outside. Delta S of outside is going to be equal to minus delta Q of the reaction divided by temperature. So delta S for outside is going to be minus delta H of the reaction divided by temperature. Delta H of the reaction is given is minus 92.6 kilojoule per mole, and hold this one divided by 298 Kelvin. So we get delta S of the surrounding equal to 92.6 divided by 298 kilojoule over mole Kelvin. Delta S of the system is given and is equal to minus 199, but the unit is joule over mole to Kelvin. Okay, please put a star and call it 1 here, put a star there, call it 2. You cannot add 1 to 2 because 1 is dealing with kilojoule and the second one is 1,000 times smaller than it, or I should say bigger, because we multiplied it by 1,000 to get the joule. I need them to be the same unit. So one way is to transfer first one to joule, or the second one to kilojoule. I'm going to divide this one by 1,000 to get it in kilojoule. So this one, if you divide it by 1,000, it will give you minus 0.199 kilojoule divided by mole to Kelvin. Simply, I divided by 1,000 to transfer to kilo. So delta S of the system plus delta S of the surrounding we get it's going to give us actually delta S of the system, or was it minus 0.199 plus delta S of the system is a positive number, the surrounding is a positive number, so delta S universe, which is equal to this number, go with positive number. So is the reaction spontaneous? Yes. The answer is going to be yes. Process is spontaneous because delta S for the universe is a positive number bigger than 0. Okay. What's the problem that we have till now? If you want to figure whether one reaction is spontaneous or not, you need to calculate the total delta S or delta S of the universe. And then you can judge about the reaction. That's hard. Okay, let's find one way to calculate delta S. Let's find one way to judge or predict whether one reaction is going to be spontaneous or non-spontaneous, and under both standard condition and non-standard. Okay, standard and non-standard. I go with this. So we had delta S for the universe is equal to delta S of the system plus delta S of the surrounding. We know delta S for surrounding, we can get it through this, minus delta H of the reaction divided by temperature. So whatever we have delta S of the surrounding, I'm going to replace it by this. Call this one 1, call this one 2. So we get delta S of universe is going to be equal to delta S of the system. Then it will be minus or plus minus delta H of the reaction divided by T. I call this one 3. Multiply number 3 by T, by minus T. I get minus T delta S universe minus T delta S of the system. And here I will get minus to minus, it will be positive, and T by T will be cancelled. So I get plus delta H of the reaction. Call it 4. Rearrange this one. You get minus T delta S of universe equal to delta H of the reaction minus T delta S of the system. The left part, we call it change gives the free energy. So you call it gives free energy. And we show it by delta G. So I get delta G equal to delta H minus T delta S. So we get delta G equal to delta H minus T delta S of the system. So you want to find, let's go with here. You can call this one system again, system. If this one is system, let's call it system. So delta G is going to be delta H of the system, not the reaction, because I call this one system. What's a good thing about this formula? This formula, you can use it to predict whether one reaction is going to be spontaneous or non-spontaneous by finding G. And I can use any condition. Why? Because there is a place for temperature. I can apply any temperature here and predict the delta G. Okay, that's the beauty of this formula. If delta G equal to 0, we say we are dealing with equilibrium. Okay. We have two processes. One is taking reactant to product, and the second one is taking the product back to reactant. We showed that one by double arrows. Delta G is 0. Rate of the forward reaction equal to rate of the reverse reaction. you're not gonna get or lose heat. You're not gonna get or lose heat. If delta G is negative, then we're talking about a spontaneous process, spontaneous reaction. If delta G is positive, so first one, if delta G is negative, spontaneous, delta G is positive, then it will be non-spontaneous. So delta G equal to delta H minus T delta S. This is number 5. Okay. So I'm going to write it here. Delta G, which is change with Gibbs free energy, it's going to be equal to delta H minus T delta S. Let's call it 1. And this is the system. Delta G is a state function. That means delta G, you can write it as change with Gibbs energy of the product minus change with Gibbs free energy of the reactant. Okay, or G2 minus G1, final minus initial. Okay. So I can go with this one. I can go with delta G equal to, similar to delta H, number of mole of reactant product multiply delta G of product minus number of mole of reactant is delta G of the reactant. But I'm using a standard condition for reactant and product, so I need to put the same thing here. Okay, I need to do the same thing. Okay. Let's call this one 2. What's the difference between 1 and 2? Delta G standard, you have to use it only and only for this condition. And concentration equal to 1 mole over liter. Only when you are dealing with this condition, you can use this formula. The bad side of it, you're stuck with this condition. It's really easy to use, but only for a standard condition. But the next one, I remove the standard condition and I say delta H minus T delta S. The good thing with this formula, you can use it for any temperature, any condition. Any condition, that one is going to give you delta G of the reaction. So if you go with delta G of the reaction, this is going to be delta H of the reaction. That one, this will be T delta S of the reaction. Here, if you say delta G of the reaction, and then it will be delta G of the product minus delta G of the reactant. Okay, for any condition, second, first one only for the standard condition. This one only for the standard, for any condition. Okay. So let's close the discussion by 2 examples. First example, we have 2 mole from nitric acid. We add NO, the gas phase. We get 3 mole NO2 plus 1 mole H2O. Delta H for the reaction is given. Delta S of the reaction also is given. So this one is going to be delta H of the reaction, and that one is delta S of the reaction. Now they are saying find delta G, and please ignore the K. Find delta G. Okay. They want to go through the K because in like at least in Chem 1414 we don't cover equilibrium, and this chapter is completely different one, so I don't want to go in K. Okay, how to find delta G? Delta G, you go with delta H minus T delta S. You need to be careful about unit. Unit for delta H is given in kilojoule per mole. You subtract it, here you subtract temperature multiplied delta S. Temperature, it comes with Kelvin. You multiply it by delta S. Delta S is given in joule over mole to Kelvin. Kelvin by Kelvin, it will be cancelled. So you get kilojoule over mole minus joule over mole. And this is wrong. You cannot subtract two numbers with different unit. You either transfer the first one to joule and then subtract the second from it, or the second transfer it to kilojoule. So I need to fix it. I need to transfer one of them to another unit. Which one? Maybe, you know, like we can divide this one by 1,000. That would be easier. So I'm going to divide the delta S by 1,000 to make my life easier. So I go delta G for the reaction. It's going to be delta H 36.5 kilojoule over mole to Kelvin minus T delta S. T is 298 Kelvin multiply delta S 287.5 joule over mole to Kelvin. So hold this one, we need to divide it by 1,000 to make it easier. So I have T delta S. I'm going to hold this one separately, show you the correct answer for it. 298 Kelvin multiply 287.5 says joule over mole to Kelvin. 1,000 joule equal to 1 kilojoule. So you cancel joule by joule, and this number will be divided by 1,000. So T delta S (298) multiply 287.5 divided by 1,000. That's going to be 85.7 unit kilojoule over mole. Now I can subtract it from the first one. So I go with delta G for the reaction. First one, 136.5 kilojoule over mole. Sorry, why did I write this one Kelvin? This is wrong. Mole minus 85.7 kilojoule per mole. So minus 136.5. I got 50.8 kilojoule over mole. So 50.8 kilojoule per mole, and is bigger, is a positive number. Because this is positive number, it will be non-spontaneous. Because delta G is positive. Okay. So I showed you how to use delta G minus delta G equal to delta H minus T delta S. And now we can use any of this formula. Or delta G under standard condition for the reaction is going to be number of mole of product to delta G of product minus number of mole of reactant to delta G of reactant, call it 2. Here's a question. You are given a balanced reaction. Delta G for any one is given. They're asking what's the delta G of the reaction. Only one that is not given is this, O2. Okay. The most stable phase is going to be the reference. Remember, for O2, we said delta H of O2 is 0. You will see the same thing for delta G. Wherever delta H was 0 under standard condition, then you write the same thing for delta G. The most stable phase of any element, it has delta G equal to 0. So I go delta G of the reaction. It's going to be this. I go with 12 multiplied delta G of CO2 plus 6 multiplied delta G of H2O minus 2 multiplied delta G of C6H6 plus 15 multiplied delta G of O2. So delta G of the reaction under standard condition is going to be equal to 12 multiplied minus 394.4 plus 6 multiplied delta G of H2O. H2O is 237.2 minus 2 multiplied delta G of C6H6, which is 124.5 plus 15 multiplied 0. That one will give us the final answer. So we have 12 multiplied 394.4. And this one should be negative 2 CO2. Wait, why did I use? It's H2. This is negative. Yeah, that one is negative. Okay, so I have 12 multiplied minus 394.4, 6 multiplied 237.2. Then we get minus 2 multiplied 124.5 I got 5907. Give it a try again. 12 multiply 394.4 plus 6 multiply 237.2 minus 2 multiply 124.5. Okay, what did I make mistake? This should be multiply. Okay. Recheck it. I made a mistake somewhere. 12 multiply 394.4 plus 6 multiply 237.2 minus 2 multiply 124.5. Yeah. I got 5907 in unit, because I gave it in kilojoule per mole, so it will be kilojoule per mole. Okay, kilojoule per mole. So I showed you how to use the delta G in two methods. Delta G at the end is negative, so it will be, because it's a negative, it will be spontaneous. Reaction, it will be spontaneous. Okay, so I'm done with this lecture. I hope it was useful, and I wish you all the best, guys. Take care.